Yeah, we do not use vacuously true implications.
Sorry, I was just
We don't use vacuously true implications in our sciences. That's true. All right, so let's do a quick run through of everything that we covered last time. So we're coming at logic and we're coming at it sententially. We're starting with language and we're stripping away the pieces of language that can encode our logic. And so we already talked about in our logic, we're not interested in every single sentence you can compose. We're interested in sentences that encode a proposition, sentences that we can call true or false. Those types of sentences we call statements. Now, from here on out, we're going to use sentence and statement interchangeably. It's understood when I say sentence, I mean statement. I'm going to do that simply because the author does that. So from here on out, sentence means statement. And we won't distinguish between the two anymore. So what is a statement? A sentence that's either true or false, not both. From here on out, we'll use sentence and statement interchangeably. Now, last week we introduced you to truth, functional, sentential connectives. These are sentential connectives that you can add on to statements. And the truth or falsity of the resulting statement is a function of the truth or falsity of the component statements. And the 5 that I told you we're pretty much interested in are and, or, not, implies, and equivalence. That's pretty much the only 5 we care about. So let's set some up here. So alpha and beta are going to represent statements. I know alpha is a statement, I know beta is a statement. That's all I know about it. So if I say alpha is a statement, it has to be true or false. It has to be one or the other. Similarly, if beta is a statement, it has to be one or the other. So if I have 2 statements, we have 4 possible combinations. Either both the statements happen to be true, either the first statement happens to be true and the second statement happens to be false, the first statement happens to be false or the second statement happens to be true, or both statements happen to be false. It has to be one of those 4 possibilities. Those are the only 4 possible outcomes. And so we said that and is truth functional, meaning that if you take 2 statements and you AND them together, and I tell you the truth or falsity of the component statements, you should be able to determine the truth or falsity of the entire resulting statement. So I tell you alpha is true and beta is true. So now the new statement, alpha and beta, is true. And you were able to determine that simply by knowing if these were true. That's what it meant to be truth functional. The truth or falsity of this is a function of the truth or falsity of its component statements. Next one, if alpha is true and beta is false, alpha and beta is false. False. I say I'm a teacher and I'm a billionaire. Did I lie to you? Yes. Next one, if alpha is false and beta is true, alpha and beta is false. And finally, if they're both false, then it's false. Good. Now moving on to or. Remember, we're using or in the inclusive sense of the word. So it's okay to have both alpha and beta be true. So if I tell you alpha is true and beta is true, alpha or beta is true. True or false is. False or true is. And false or false is false. All right. So now implies, the trickiest one of them. So true implies true is true. True implies false is false. False implies true is true, vacuously true, and then false implies false is also vacuously true. So those are our 2 vacuously true ones. Now, equivalence. What did it mean for alpha and beta to be logically equivalent?
They have the same truth value?
They have the same truth value. Either they're both true or they're both false. That's what it means for them to be equivalent. So if alpha is true and beta is true, are alpha and beta logically equivalent? Yes. Is true logically equivalent to false?
No.
No. Is false logically equivalent to true? No. Is false logically equivalent to false? Yes. And then, forgot to do my not, so I'll put the not at the end. Negation. The negation of true is just false. Negation of true is false. Negation of false is true. True. And similarly for beta, false, true, false, true. So really quick, that's what those symbols mean. And there's our 5 basic symbols. Good so far? Any questions on those? Now some of the basic things we proved last time. Remind you of it. If you negate alpha and beta, negating a conjunction, it turns the and into an or if you distribute the not over it. If I distribute a not over an and, it converts it into an or, right? And so here's not alpha and beta. let's see, we have alpha and beta right here. So I did everything in the same order, so this is just a negation of that. So this is false, true, true, true. Let's rethink this through in our intuition and hopefully it clicks. So not alpha is false. False or false is
False.
false. Now, false or true is true. True or false is true. And true or true is true. So it came out the same. Now, since these two things give the exact same values, no matter the input you give them, they are logically equivalent. They're saying the same thing. This is logically equivalent to that thing, and this is logically equivalent to that thing. It's two different ways of writing the same expression. So over here, let's try another one. We also went over the fact that when you distribute a not over an or, it turns it into an and. So this one is just negating this column. So we have false, 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 true. And now let's think this one through. So false and false is
False.
false. False and true is
False.
false. True and false is
False.
false. And then finally, true and true is.
True.
And surprise, surprise, they come out the exact same. So they're logically equivalent. In other words, what I mean by they're logically equivalent is if I were to write out a new column here, and my new column was this, not alpha or beta is logically equivalent to not alpha and not beta. So if I wrote a new column here in my truth table and we evaluated this thing, what is this thing saying? It's saying that this gives out the same truth or falsity as this. When would it be true? Would it be true in this case?
Yes.
Would it be true in this case?
Yes.
This case?
Yes.
This case?
Yes.
So it would be what we call a tautology. It's always true. It's never false. So that's what we're saying. When we're saying these two are logically equivalent, we're saying if you were to set up the equivalence operator between the two, you would get true, 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 all the way down. That's what it means. Okay, and then some other ones that we talked about. Here's alpha implies beta. I just re-stuck it out of there right there. So alpha and beta, here's all our possible combinations. Here's alpha implies beta. Let's fill out beta implies alpha. So true implies true is true. False implies true is true, vacuously true. True implies false is false. And then false implies false is
True.
vacuously true. And so notice that these two are very different columns. This one's false when this one's true. This one's true when this one's false. One of the most common mistakes in logic is confusing alpha implies beta with beta implies alpha. They say different things. Now let's look at not beta implies not alpha. We remember what we call this? This is the contrapositive of this. If this is alpha implies beta, this is its contrapositive. So now, looking at this one, false implies false is true. True implies false is false implies true is true, vacuously true. And then true implies true is true. And so notice that the contrapositive gives you the same thing as the implication. Alpha implies beta is logically equivalent to not beta implies not alpha. They give you the exact same output. Saying if there's fire, then there's oxygen is logically equivalent to saying if there's no oxygen, then there's no fire. Logically, they say the same thing. And now, finally, let's AND these two together. So this was alpha implies beta, and this was beta implies alpha. What if I have alpha implies beta and beta implies alpha? So I'm ANDing these two columns together. True and true is true. False and true is false. True and false is false. ANDing together a true and false statement, false. And then true and true is true. So notice that it spit out true, false, false, true. Same thing as logical equivalence. So one of the ways we think about logical equivalence is it's saying alpha implies beta and beta implies alpha. That's where it gets the back and forth arrow. It's saying this implies this and this implies this. That's why that symbol is what's used. Okay. Precedence. When you're evaluating one of these expressions, the precedence is you do your nots first, then your ands, then your ors, then your implies, and finally your logical equivalence. When you're doing the algebra of it, so to speak. So, if you were to see the expression alpha or beta and not alpha, and I were to put all the parentheses on there to make it completely clear how you read that, it's alpha or, first we evaluate the not, so not alpha, then we evaluate the and then finally the or. So first your nots you kind of think about like negative signs, your ands you kind of think about like multiplies, your ors you kind of think about like pluses, this you kind of think about like equals, and we don't really have a good one for implies. Here's another one. If I say alpha implies beta is logically equivalent to not beta implies not alpha, and we put all our parentheses on there, what do we do first? Our nots, so put parentheses around that, then our implies, and then finally our equivalence. So, going to do a concrete example now, working through one of these expressions, simplifying it. This would be just like on your algebra test. If you got an algebra test and it was like something like 6 plus 4 times negative 9 divided by 7 equals da-da-da, evaluate it. This, we're going to evaluate this expression, and it should come out to true or false. So I gave two sentences here. The first sentence, Newton was born in 1642. That happens to be true. Our second sentence, G, is going to be Galileo died in 1640. That's a false sentence. So now we're going to evaluate this expression and determine if it's true or false. You do it the same way you do your algebra. First we do our inner parentheses. So N was true and G was false. So go ahead.
N or G would be true.
True, perfect. So evaluating that we get true and not. Let's plug in our N. False. Implies. Maybe you can just do this one as you go. What is false implies true?
It's true.
True. And we still need to evaluate this thing. Now, not false is the same thing as?
True.
And true is? So we get true implies true. And true implies true is? True. So this whole evaluation, this whole expression evaluates to true. Just like if I gave you a bunch of numbers and operations on the numbers, you could evaluate it and one number would come out. Similar type thinking. Okay. So now, definition of what we call an atomic sentence. What is an atomic sentence? It is a sentence with no sentential connectives. In other words, it's like the simplest kind of sentences we can have out there. They operate as an atom. You can't break it up anymore. It's as simple as a sentence can get. So, example of an atomic sentence. The sky is blue. There's an atomic sentence. There's nothing that you can strip out of there without making it meaningless. If I get rid of blue, then it's saying the sky is. The sky is what? So let's go on to another one. The sky is not blue. Is this an atomic sentence? No. What can we get rid of? Not. We can get rid of the word not. We change the meaning of the sentence and get rid of the word not, but it's still a sentence. Or in our case, it's still a statement. It's still something you can call true or false. Here's another one. 1 plus 1 equals 2, and 9 is less than 3. Atomic sentence? No. This is an atomic sentence, and this is an atomic sentence, but adding them together is definitely not an atomic sentence. Next one. Donnie thinks cake is good. No, you can get rid of Donnie thinks.
It's because it's a.
It's kind of like the one we talked about last time was Jack believes.
It depends on what you think, and that's why we can't use it.
Well, that's why it wouldn't be a truth functional sentential connective, but it's still a sentential connective. Cut it off.
Would be a problem.
And we're still good.
A predicate sentence.
We'll get the predicates later. Not going to talk about now.
And that's why this doesn't work.
No, this has nothing to do with predicates.
Okay.
Okay, so what's an atomic sentence? It's one that has no sentential connectives. You've somehow gotten down to the simplest form of the sentence that's possible. Atomic sentence. Okay, a sentence is now a tautology if it is true independent of the truth value of its component atomic sentences. A sentence is a tautology if it is true independent of the truth value of its component atomic sentences. Here, wrote out some examples. We're going to look at each of these is going to be a tautology. This one is P or not P, assuming P and Q are atomic sentences. P or not P is going to be a tautology. I tell you, the sky's blue or the sky's not blue. That's always true, regardless of whether or not the sentence, the sky's blue, is true or false. I say 2 plus 2 equals 19 or 2 plus 2 does not equal 19. That's true. So this is going to be a tautology. No matter the truth or falsity of P, this whole thing can be evaluated to true. Here's another one. P and Q implies P. No matter the truth or falsity you plug in for P and Q, when you write out its truth table, it's going to be true, true, true. And similarly for this one. So we're going to write out the truth tables and actually see this in action. So doing the first one. So we've got two atomic sentences here, P and Q. And so we only have 4 possible combinations. We have P's true and Q's true, or P's true and Q's false, or P's false and Q's true, or they're both false. Has to be one of those 4 cases because P and Q are sentences. Atomic sentences, but sentences. Things that we can call true or false. So, let's look at this case. So if P's true, true or false is true. And that's the same value for P. False, so false or not false is the same thing as false or true. And false or true is true, and false or true is true. So it's true, 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 no matter what you plug in there. Let's try another one. This is P and Q implies P. So true and true is true, and then true implies true is true. So the whole thing evaluates to true. Next one, true and false is false. False implies anything is true, vacuously true. False and true is false, and false implies anything is true, vacuously true. And false and false is false implies anything is true. So, tautology. It's always true regardless of the truth or falsity of the statement. If I tell you the sky is green and 2 plus 1 equals 7, I tell you, if the sky is green and 2 plus 2 equals 4, then the sky is green. My overall statement was true. It was a tautology. Let's try the last one. All right, so we're ORing these two together, and then we'll see if P implies it. So true or true is true, and then true implies true is true. Okay? True or false is true, and then true implies true is true. All right, next one. False or true is true, and then false implies true is vacuously true. And then P again here is false. False implies anything, true. So those were all tautologies. No matter what sentences you plug in for P and Q, as long as you plug in sentences, things that are true or false, the result will be true or false if you give your sentences any of those forms, any of that sentence structure.
Out of curiosity, is there a method for solving tautologies in more complex situations, or is it generally just a brute force?
We'll get to that. Solving tautologies in general. So what we are going to be very interested in is demonstrating that something is a tautology, in particular implications. That's all we pretty much care about in axiomatic systems, is showing some implication is tautologically true. What does it mean to prove the Pythagorean theorem? It means to demonstrate that the Pythagorean theorem is a tautology. It's tautologically true. And you're right, we cannot just rely on truth tables. Truth tables work in nice simple cases. As the number of terms we use, imagine now that I were looking at some expression that had 10 variables in it.
It's exponentially more.
Yes, it's growing exponentially. If we only had one sentence that we had to look at, I don't have an example up here, then we'd only need 2 rows. If we have two atomic sentences, then we need 4 rows. What if I had 3 variables? Now I need 8, 4 variables. 16, all the way 10 variables, I need 1,024 rows to evaluate that thing. It blows up quickly. So truth tables, they're wonderful for nice, simple demonstrations that we want to do. But we're going to introduce rules of derivation so that we don't just have to rely on truth tables. And plus there's going to be things that we're trying to prove that turns out truth tables can't handle anyways. So you couldn't prove something like the Pythagorean theorem with just a truth table. It's not even possible. It's not a matter of being really, really hard and you have to use 20 trillion columns. It's not possible. So, truth table is a great place to start. If you can use a truth table in a simple way, do it. But we have other things to fall back on, which is what logic is developing. Okay, so gave you intuition for what a tautology is. Here's now our definition of a tautology. What is a tautology? A sentence is a tautology if and only if the result of replacing any of its component atomic sentences in all occurrences by other atomic sentences is always true. If no matter how you replace its atomic sentences, the result is always true, then you have a tautology. Now we had to put one little limitation on there. We said in all occurrences, which means if I replace one variable with a sentence, I have to replace the same variable with the same sentence again. We'll see concrete examples. We should see concrete examples. Did I not write any up here? Oh, they're right here. So, we'll see it from these two useful observations. So there's our exact definition of a tautology. If, no matter how you replace its atomic sentences, as long as you replace it in all occurrences, the result is still true, you have what's called a tautology. And we already talked about the limitations of truth tables. We can't prove everything with truth tables. We can't prove all tautologies with truth tables. Great place to start that. So now, two useful observations. Our first one. A sentence which is not a tautology may become one upon the substitution of a compound sentence for atomic ones, or the substitution of the same atomic sentence for a distinct one. So let's see both those in action. That's a lot to take in. Alpha implies beta. Is this a tautology? No, it's possible for that to be false. Right? You write the truth table for alpha implies beta. Here it is. We have a false there. So no, it's not a tautology. However, if I do an interpretation where I now replaces beta with gamma or not gamma, so here is an interpretation of it. I replace beta with something that has more structure. I replace an atomic sentence with a compound one. Now look at this. Alpha implies gamma or not gamma. Notice gamma or not gamma is always true. And anything implies true is always true. If alpha is true, true implies true is true. If alpha is false, false implies true is true. And so by replacing beta with something that had more structure, we took something that wasn't a tautology and turned it into a tautology. Similarly, let's take alpha implies beta, and if I replace alpha and beta with the same sentence, the result is also a tautology. So read this one more time, and I think it'll make sense. A sentence which is not a tautology may become one upon the substitution of compound sentences for atomic ones, or by the substitution of the same atomic sentence for distinct ones. Good? And now coming back up to a tautology, and maybe reading a tautology one more time will make sense. A sentence is a tautology if and only if the result of replacing any of its component atomic sentences. So if neither of those are a tautology, I'll come back and say that after we go over those examples. That'll be a better time to do it. Sorry. So here's our second useful observation. So our first one is, if we do these substitutions, we can turn things that are not tautologies into tautologies. Second observation. A sentence that is a tautology remains one upon the substitution of any sentence for its atomic sentences, as long as you do it in all occurrences. So we already proved that these things right here, each of these were a tautology, right? Oh, bear with me my camera before I go over. A little more. Oh, there we go. Can I read those rules? Yes. Okay. So we've already proved that P implies P or Q is a tautology. So this right here is a tautology. Now what this is saying is that a sentence that is a tautology remains one upon the substitution of any sentence for its atomic sentence. So if this is a tautology, I should be able to replace P and Q with any sentences I want, even if they have more structure, and the result should still be a tautology. So if I let P be X and Y implies Z, so it's all that, and I let Q be not X or Y, plugging that in for P implies plugging that in for P or plugging that in for Q. This new result is for sure going to be a tautology. How do I know that it's for sure going to be a tautology? This whole thing right here has to be true or false. Right? And if this whole thing is true, then this whole thing is true. And if this whole thing is false, then this whole thing is false. So if we call this chunk right here P, then we say if P is true, and notice that this whole chunk has to either be true or false. So call that P, call that Q, and then it's just this truth table right here. If this whole thing evaluates to true, and this whole thing evaluates to true, and this whole thing evaluates to true, that's doing this top row, we get true. If this whole thing evaluates to true, and this whole thing evaluates to false, that's exactly what this would be. So you can add more structure to a tautology by replacing its atomic sentences, and it's still a tautology. That was the observation. So now let's read our definition of a tautology one more time, now that we've had that example, and hopefully it all clicks. So a sentence is a tautology if and only if the result of placing any of its component atomic sentences, P or Q in that case, in all occurrences, meaning I can't replace P with one thing and this P with another thing. Otherwise, I might destroy the tautology. So, if and only if the result of replacing any component atomic sentence in all occurrences by other atomic sentences is always true. Good? Okay. Now we have the notion of a tautological implication. Go ahead.
The definition. Okay, never mind. I'm good.
Okay. So, two more words that we're going to use a lot. Tautological implication. What's a tautological implication? It's an implication, that's a tautology. If P implies Q is always true, it's a tautological implication. That's all we mean by tautological implication. Similarly, what's a tautological equivalence? It's an equivalence, that's always true. This right here is a tautological implication. This messy thing that we wrote right here is a tautological equivalence. If we did the truth table for that thing, it would be true, 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 true. So that's tautological implication and tautological equivalence.
Is there a word for like not X and X, or X, not X or X? Is a tautological, but it's not implication or equivalent.
You're saying X or not X?
Yeah, it's tautological, but it's,
That's a tautology.
yeah. I was just wondering if there's a word, phrase for it.
No, it's just that we are particularly interested in tautological implications and tautological equivalences.
Okay.
These are the ones we care the most about. Remember, this one is just encoding two tautological implications. It's saying this tautologically implies this, and this tautologically implies this. That's what it's saying. And so what we really care about is tautological implications. Again, can't overstress it. Every theorem in math, when we say we proved the theorem, what we did is we demonstrated that the implication is a tautological implication. That's what it means to do it. All right. So we've talked about limitations on truth tables. And we don't want to use truth tables to prove everything out there that we can prove. We want to come up with rules of derivation, basically rules of deductive reasoning that we can apply to come to know things are true, and not just rely on truth tables to do it. It's very limited to use truth tables. So we're going to talk about our rules that we want to develop to help us prove things. Now, these rules need to follow two, we have this criteria, two major criterions that we want all our rules to follow as we develop them. So criterion 1, given a set of premises, the rules of logical derivation, yet to be stated, they're over on the whiteboard if you care, the rules of logical derivation must permit us to infer only those conclusions which logically follow from the premises. That's one criterion we want for our rules of logical inference. Given a set of premises, the rules of logical derivation must permit us to infer only those conclusions which logically follow from the premises. We don't want to be able to conclude something that doesn't logically follow. Similarly, criterion 2 says the exact same thing, replacing the only with an all. Given a set of premises, the rules of logical derivation must permit us to infer all those conclusions which logically follow from the premises. And that's going to be our criteria that we're going to use two criteria that we're going to use to help us judge rules and make sure that we're not picking up bad rules. Now, there's a bit of a problem here because I use this phrase logically follows. What am I saying? I'm saying my rules of logical derivation must logically follow. Isn't that just circular? And I'm pretty much saying nothing. So far, you'd be pretty justified in thinking that. I'm saying my rules of logical derivation have to logically follow. Well, then what does it mean to logically follow? And so we have to come up with a definition and a notion of what it means to logically follow sententially. And then if I can explain what it means to logically follow, then now this can make sense. And the rules of logic have to logically follow whatever that means. So you shouldn't be happy until I can explain to you what logically follows means, and then you can accept this. So still need to justify that. Okay, oops, I've been using the word interpretation, but now we introduce it. Sentential interpretation. A sentence, P, is a sentential interpretation of Q if and only if P can be obtained from Q by replacing the component atomic sentences of Q with any other sentences. This sentence down here is an interpretation of this sentence right here. Read it one more time. A sentence P is a sentential interpretation of Q if and only if P can be obtained from Q by replacing the component atomic sentences of Q with any other sentence. So in our example, this would be like the sentence Q, this would be P. This is an interpretation of this because I can get this by replacing atomic sentences in here with other sentences. Maybe atomic sentences, maybe more complex ones. In that case, it was more complex. So, a sentence P is a sentential interpretation of Q if and only if P can be obtained from Q by replacing the component atomic sentences of Q with any other sentences. That's what it means to be an interpretation. Okay, so now, to be an interpretation, P must preserve the form or the structure of Q. If I somehow destroy structure, it's not an interpretation. So this is an interpretation of this because notice all the structure that this had is preserved. This is saying something implies something or something. This is saying something implies some disjunction. This is saying something implies some disjunction. So if it is a proper interpretation, if it is a sentential interpretation, it has to preserve that structure. You cannot lose structure in an interpretation. You can add more structure, you can never lose it. Okay. So, I'm going to give, this is my Q, and tell me if this is interpretation, and then this is my Q, tell me if this is interpretation. So starting with Q here, Q1, if the sun is shining, then Marianne is happy. So there's our first sentence. Question, is P an interpretation of that? So what does P say? It says, if 2 plus 1 equals 4, then snow is black or I'm a fool. Is this a sentential interpretation of this?
No.
Can I get this by replacing atomic sentences here with other sentences?
No, well, okay. I would say no, because I think that the snow is black or I'm a fool is 2 different atomic sentences.
You are correct that this is 2 different atomic sentences. However, we are only replacing one sentence with it. So I take this atomic sentence, the sun is shining, and I replace it with this atomic sentence. And I take this atomic sentence, and I replace it with a disjunction, but I didn't cut out any structure. All the initial structure is there. That's very similar to what we did going from here to here. I added more structure. I didn't remove any structure.
Okay.
That is a valid interpretation. Let's try the next one. So, Q2 says, if the sky is blue, then it's raining outside or the sky is blue. My proposed interpretation is, if 2 plus 1 equals 4, then snow is black or I'm a fool. Is that an interpretation?
No,
Why not?
because the sky is blue and the sky is blue over there needs to be the same sentence.
Yes, we have to replace it with the same sentence. If I replace the sky is blue with 2 plus 1 equals 4 here, then I have to replace the sky is blue with 2 plus 1 equals 4 here in order for it to be a valid interpretation. Since this does not do that, even though it has the same structure, it is not an interpretation. You have to replace the same sentences with the same sentences if you're going to replace them. Okay, so now we're ready for our notion of what it means to logically follow. Q logically follows from P if and only if every sentential interpretation of P implies Q is true. So we now have a notion of a sentential interpretation, and now if every sentential interpretation of that is true, then Q logically follows from P. There is no interpretation you can find of this sentence that makes it false. No matter what sentence you replace P with and what sentence you replace Q with, if the whole result is still true, then we say Q logically follows from P.
When in this context, are you saying that P implies Q is being evaluated to true?
Yeah, we evaluate that to true. That's the way you can say it.
Okay.
So Q logically follows from P if and only if every way you evaluate the implication, it comes out true. That's one way to say it. But you get to do more than just evaluate the expression plugging in trues and falses. You get to also replace P with something that has all sorts of substructure, and it still better hold. So it's not just replacing atomic sentences with atomic sentences. You can replace atomic sentences with any sentences you want. So you can add tons of structure. But as long as you don't remove the structure that was already there, then that counts as interpretation, and Q will logically fall from P. If no matter how you do that, it stays true. We'll get more concrete examples of this. So now, a logically equivalent way to state what a tautology is. We had our tautology stated somewhere over there.
It's over here.
Over here off the board. So a sentence is a tautology if and only if the result of replacing any of its component atomic sentences in all occurrence by other atomic sentences is always true. Logically equivalent way of saying the exact same thing. A tautology is a sentence whose atomic sentential interpretations are all true. If no matter how I replace atomic sentences with atomic sentences, it's all true. It's saying the exact same thing. It's just using this interpretation language now, a sentential interpretation.
That's where I was actually thrown off. Why are we using circular definitions?
We're not. Where's the circle?
Oh wait.
It would have the major criteria thing, but then he defines logically follows.
Why do I keep seeing it and then I lose it? Never mind.
Tell me if you see any circular reasoning, because then I'm not explaining something enough.
Oh, you did. For some reason okay, never mind.
Okay, so now, note that if every atomic interpretation is true, then every interpretation is true. So if, no matter how I replace P and Q in this, the result is always true, then if no matter how I replace P and Q with true or false in this, keeps it true, then no matter how I replace P and Q in this with new sentences that have even more structure, it will still always be true. So if every atomic interpretation is true, then every interpretation is true. If no matter how I replace P and Q in there with true or false, keeps the whole result true, then no matter how I replace P and Q in there with entirely new sentences, the result will still always be true. Because the entirely new sentences still have to evaluate to true or false. So you're still just plugging in true or falses in a more contrived way. Okay, so criterion for something logically following, Q logically follows from P then, if P tautologically implies Q. So if P implies Q is a tautology, we are now justified in saying P logically follows from Q. Q logically follows from P. Q logically follows from P if we can show P implies Q is a tautology. Make sense? So that is how we're going to come up with what logically follows and our rules of logic. We simply demonstrate that they're a tautology, and we use truth tables to do it. So let's now do our first concrete example, and I think it will help all of this make more sense. Examples help a lot. So here we go. Setting up some small argument. Premise 1. Either Mary gives Peter his toy, or Peter cries. That's going to be our first premise. Premise 2. Mary does not give Peter his toy. What can we conclude?
Peter cries.
Peter cries. And now we're going to prove that that actually follows. Okay, so encoding this first sentence here, I'm going to use M for Mary gives Peter his toy, and I'm going to use P for Peter cries. So this says M or P, and this says not P. See it?
Not N.
Right here, yeah, that's,
Oh, thank you. Yes. Good catch. So, encoding that here, we're saying Mary gives Peter his toy or Peter cries, and Mary does not give Peter his toy. Now, you were able to come to the conclusion, therefore Peter cries. We're going to prove that that's a valid conclusion that you come to. So, how do we do that? So, either Mary gives Peter his toy. So, Mary gives Peter his toy is a statement. It's a sentence. It has to be true or false. Either Mary does give Peter his toy or she doesn't. So, we know that Mary gave Peter his toy and Peter cried. Well, just writing out all the truth or false values here. Don't want to say it out loud in case it trips you up. Okay, so here's our all our possible combinations for what could have happened. Right? Now, M or P is ORing these two together. So true or true is true. True or false is true. False or true is true. False or false is false. Not P right here is just negating this.
False, true. False, true.
Perfect. And now, M and P and not P, this is anding together these two. Sorry, I think I called that and. M or P and not P is just anding these two together. Right? So, true and false is,
True.
I'll say on this side. True and false is false. True and true is,
True.
true and false is,
False.
false and true is.
False.
Alright, now finally, this is saying this whole thing implies P. This whole thing implies P. So false implies true is true. True implies false is.
False.
Oh, I messed something up.
Yeah, because you used not P again
Yeah,
on every single one of those.
instead of not M. Yeah.
You're saying I messed up on these ones?
So clear up at the top of your thing. You got not P instead of not M because you messed up.
Oh.
Yeah, with your premise.
Thank you. That was a not M. Good old logic.
That's all
Has to work out
that's
in
on
the
the other one too, isn't it?
Yeah, yep. It's on all three.
end.
I was
Oh, then we gotta
confused where
switch
you're
those,
getting
yeah.
these structures from.
Okay.
Okay, wait, then you gotta change the not N.
I've got to change the what?
Not N, like the whole.
Right. I've got to redo this column is what you're saying, right?
Yeah, yeah.
And that will change this column. Okay. Sorry about that. Okay, not M. So we're going to get false, false, true, true. Over here now, we were anding these two together. False, false, true, false. And now finally, we're saying this implies P. So false implies true is
True.
true. False implies false is. True implies true is.
True.
And false implies false is.
True.
Okay. And surprise, surprise, it comes out a tautology. Which means that this is always a valid argument, no matter the truth or falsity of this. So we saw this rule in action with our intuition. We knew M or P must, if I know M or P is true, and I know that not M is true, or in other words, M is false. If I know M or P is true, and M is false, then P must be true. Right? Intuitively, we can see that. That's saying this exact same thing. This and this implies this is a tautology. That's what you're doing in these arguments. Your intuition was able to make the leap that this and this together implies this will always be the case. And your intuition is correct. So what we did in that proof is we showed that using different symbols, but the exact same thing. Alpha or beta, and not alpha implies beta, that whole thing, is a valid rule of logic. It is a tautology. It is always true.
A valid rule of logic is a tautology, is what you're saying?
Yes.
Every time.
It logically follows. This beta logically follows from this.
Okay.
And so I will use a valid rule of logic for our things that we show to be tautologies. We're going to talk about two different types of rules. We're going to talk about our valid rules of logic, and then we're going to talk about our rules of derivation, our rules of deductive reasoning. We can use our rules of logic in deductive reasoning, but these are going to go beyond just logic, beyond just truth tables, because truth tables aren't sufficient for everything we want to do. But early on it will be for everything we're doing. So here's an example of a simple argument. Good? So now, let's introduce you to the rules of deductive reasoning and then go through actual proofs. And then a few proofs really just brings everything home. So, let's move that over. I don't know if I'll need to reference that. Okay, so restating criterion 1. Here's usefully what criterion 1 is telling us over there. Usefully, because what criterion 1 said is our rules of logic should only enable us to determine those things which logically follow. Where is it? It's right here. It should only give us those things which logically follow. So using criterion 1, what that means is if a new rule of logic would allow us to derive a false conclusion from a true premise, we reject it. That should never be possible. So it gives us a system for rejecting our rules of logic. The ones that we don't want. The ones that we're going to say that's not a valid rule of logic. If it ever allows this to happen, then we know that we cannot use it as a rule of logic. So over here we discovered a rule of logic, and this is now a valid rule of logic and we can use it. Let's look at some other ones and try and determine if they're valid rules of logic. So, question. If I know beta and I know alpha implies beta, can I conclude alpha? Does alpha logically follow from this? Is this implication a valid rule of logic to use? Is it a tautology that's always true? What does it mean for it to be a tautology? It should mean under every interpretation, it comes out true. If I can find a single interpretation that makes it false, throw it away. It can't be a valid rule of logic. So let's test it. I'm going to let alpha be Donnie is in Alaska, and beta be Donnie is in the US. So, now let's read this. This says, if I know that Donnie is in the US, and I know that Donnie being in Alaska, well, let me ask you a question. True or false? I'm in the US. True. True or false? If I was in Alaska, I'd be in the US. True. True or false? I'm in the US, and if I were in Alaska, I'd be in the US. And then finally, conclusion, I'm in Alaska. False. So I had true premises, my premises were completely true, and yet my conclusion was false. So this is not a valid rule of logic. It is not true that if you know beta and you know alpha implies beta, then you can conclude alpha. Let's try another one. What about alpha and alpha implies beta? All implies beta. If I know alpha is true, and I know alpha implies beta, do I know beta is true? Yes. What does this say? This says if alpha is true, then beta is true. And this says alpha is true. So if I know if alpha is true, then beta is true, and I know alpha is true, then I must know beta is true. So this one would be a valid rule of logic. And we could write out a truth table for it if we weren't convinced. All our valid rules of logic, we should be able to write out truth tables for. Our invalid ones, if we tried to write out a truth table for, we would end up with a fault somewhere in the column. It wouldn't be a tautology. If we wrote out a truth table for this, it would be true, 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 under every interpretation. Next question. So that's criterion 1. Why on earth do we need criterion 2? What does criterion 2 say? It says, given a set of premises, the rules of logical derivation must permit us to infer all those conclusions which logically follow from the premises. What does criterion 2 add?
Like every possibility.
Yeah, it's not limiting our rules of logical inference. Notice that if I just had alpha implies alpha as my only rule of logic, what could I conclude? Hardly anything. This is a valid rule. Is it true that if you know alpha, then you know alpha? Yes. But if this was the only piece of reasoning I was allowed to use, I would not have even been able to come to this conclusion in this argument. Because this was using a different rule of logic. So criterion 1 is saying, you don't get to come up with any bad rules. And criterion 2 is saying, and we can use any rules pretty much that we want as long as they're valid. It's keeping it open so that we can come to all the conclusions that we need to come to. So that's why those two criteria. So let's introduce our rules now of sentential derivation and move the camera over and do a couple examples. I'll have to come over there to see all this in action. So turn on the projector, get some examples from the book. Make sure I can see that all. And I think if I stay on this side of that line, we'll be in camera. Oh, my book jumped. Okay. Let me try and make that bigger. You want to turn off this front bank. It's the one furthest from the door. I don't know. Go ahead. You can see it pretty good. Okay. So going to do our first example now of a full-fledged proof. Well, this was kind of it, but give you the syntax and everything. So our first example here, well, I'll probably say what our rules of derivation are first, and then do a quick proof. We'll first introduce these two, do the proof, and then introduce the third one as we need it. So now we know that truth tables aren't going to be sufficient. They blow up too fast. So we're not just going to rely on rules of logic to determine everything we need. We want some actual rules of derivation, or rules of proving, that we can set up that enable us to come to true conclusions from true premises. So rule P, one of our rules of derivation, rule P. We may introduce a premise at any point in our derivation. You can introduce any premises you want in a derivation, at any point you want. Rule T is we may introduce S into our derivation if it is tautologically implied by, or logically follows from, any preceding sentences, or the conjunction of any preceding sentences. So that's a mouthful. Let's see it in action, and then these will seem much simpler. So here's what we're going to prove, exactly what it says here. This example. If there are no government subsidies of agriculture, then there are government controls of agriculture. I'm going to symbolize that sentence. What's all that saying? I don't know, but the structure of it is something like subsidies implies controls. Or did it say no controls?
No subsidies.
No subsidies implies controls. So not subsidies implies controls. First sentence, right? Next sentence is, if there are government controls of agriculture, then there is not an agriculture depression. So controls implies not depression. Right? There is either an agricultural depression or overproduction. So we have a depression or an overproduction. And then, as a matter of fact, there is no overproduction. So we know not overproduction. We are trying to prove, therefore, there are government subsidies of agriculture. So we're trying to prove S. And now we can close that. So what are we trying to show? I'm trying to show if we were to write out the horrendous truth table of this and this and this and this implies that, then it would be true, 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 true. But we don't want to do that. So we're instead going to use these rules to come to the same conclusion. Now, here's how this works. Some of this you're getting my own taste, my own style. You can see how the author writes these out, but it's going to be very similar. What?
You're missing the E at the end of premise.
That's okay. All right. You can read it. So, number one, we have this one premise. Not S implies C. Not having subsidies implies controls. This was a premise, so we put a P here. We use rule P to introduce this in our derivation. So I'm starting my proof. So, line 1, I introduce this as a premise. Why can I do that? Using rule P. What does this statement depend upon for its truth or falsity? What premises does it depend upon? It only depends upon itself for its truth or falsity. In other words, I know line 1 is true if I know line 1 is true. I know, mind-blowing. Let's try next one. So now, as my second line in my derivation, I'm going to introduce this premise. I'm using rule P to do that. This only depends upon itself for its truth or falsity. Similarly, I'm going to introduce my third premise, this. using rule P, and it only depends upon itself for its truth or falsity. And then finally introduce this as a premise, and it only depends upon itself for its truth or falsity. So that's where we are so far. I'm trying to use this information to prove S. That's what we're trying to do. So far, I've used rule P to introduce all my premises given to me in the problem. Perfectly valid to do. We may introduce a premise at any point in our derivation. Now, what does rule 2 say we can do? We may introduce some new sentence S into our derivation if it is tautologically implied by any preceding sentence or the conjunction of any preceding sentences. So look at this. I know we have D or O, and I know not O.
So you know D.
So I know D. How do I know that? I'm able to conclude D. That is tautologically implied by lines 3 and 4. And now, the truth or falsity of this sentence depends upon the same truth or the same dependencies that these two sentences had. So now, this depends upon 3 and 4 for its validity. If I know 3 is true and I know 4 is true, then I know 5 is true. 5 is true if 3 and 4 are true. That's what this is tracking, all the way back to our premises. Now, did you see the logic that she used just barely? If we know D or O, and we know not O, then we know D.
Are we assuming that all of these premises are tautologically true?
No, they're just premises.
How do you...
You're just going to assume that they're true for now.
When it's all said and done, I need to show that these 4 things being true implies this is true. That whole truth table is what is a tautology.
And so we're making assumptions that all of the premises are true at the moment. Is that...
Yes.
Okay.
We're making the assumption all the premises are true because imagine, let's come back over to this example when we were talking about this example. We said that if M or P and if not M, then P. You say, okay, but what if your 2 premises were false? False implies anything is true. So it's a waste of our time to even think about those cases. We just need to worry about if the premises are true, is our conclusion true? Because if the premises are false, we already know the whole implication is true. So who cares what happens when the premises are false? All we have to think about is if the premises are true, does the conclusion follow? Because if the premises are false, the conclusion for sure follows.
That makes a lot of sense.
Right, so all we have to care about is when it's true. Okay, so how do I know that this together with this implies this?
Because if it's not, if D is false, I guess, then D has to be true for 3 to be true.
Right, this says D's true or O's true. This says O's false.
So
So D is true. Or it's the exact rule that we proved right here. We already proved that that was a valid rule of logic. So we're using a rule of logic that we already proved. Anytime we use rule T here, we're using a rule of logic. And if you ever have even the slightest concerns about it, you should always be able to go to the side and quickly demonstrate it with a truth table. And so we should never be taking a step that can't be validated with a quick truth table. It should all be just simple tautological implications, just using our rules of logic. Things that can quickly be validated with truth tables. So now, we got D. Of course, we're not done. We're trying to get to S. So now I know D is true. Now what do I know? If I know D is true, what can I conclude next?
C has to be false.
C has to be false.
C has to be false.
Because that has to be true.
Yeah.
Perfect. If C is true, D has to be false. But D is true. Or another way you can think about it, C implies D is the same thing as look at contrapositive. That's D implies not C.
So not C is.
So if D is true, not C is true. Or C is false. But not C is true, right? And so I know if C is true, D is false. But I know D is true. So I can conclude that C is false. Or in other words, I can conclude not C. And this was tautologically implied by lines 2 and 5. And so now we are dependent upon whatever lines 2 and 5 were dependent upon, which is premises 2, 3, and 4. 2, 3, and 4. Okay. Next, now I know not C. What can I conclude?
The not C implies S from its contrapositive.
So I can conclude down here now
The C implies S or?
S.
That's because not C implies.
So this says
Oh, yeah.
looking at the contrapositive of this, the contrapositive of this is not C implies S. So if I have not C, I have S. You see it?
Interesting.
Or in other words, if S is false, C has to be true. But C is false. If S is false, C has to be true, but C is false. So S has to be true. Because if S were false, C would have to be true, but it's not. So sometimes you can see it. If you can't see it, we can always quickly do a truth table. That's quick. Every single one of these steps should be able to be validated with a quick truth table. And so we were able to conclude S. It was tautologically implied by which lines?
1 and
1, 2, 3, 4.
1 and 6 were the two that we combined. Typically, we're just conjoining two lines together to imply something.
Can you do more?
You can, but then you're using big rules of logic.
Okay.
And so, in general, it's nice to stick with these small rules of logic. Like if you know alpha, and you know alpha implies beta, then you know beta. That's a nice rule. Or this one. If you know M or P, and you know not M, then you know P.
And these massive rules of logic can always generally be broken down into 1 or 2.
Maybe, but even if you're using some massive rule, it should still be able to be validated with the truth table. So I would say it's a bad practice to use them. Okay, anyways, this is tautologically implied by lines 1 and 6. And so what premises is it dependent upon for its validity? It's dependent upon all the premises that we had on line 1 and all the premises that we had on line 6. So we have just barely demonstrated that if premises 1, 2, 3, and 4 are true, then S is true, which is what we were trying to prove. We were trying to prove that the 4 things I initially had here entail S, and they do. And this right here is your exposure now to completely formal proof. That's what formal proofs look like. For those of you taking geometry. Very tedious. Let's do another one. Or let's get some clarity on a rule. Can I use these rules of logic to cheat somehow? Let me set up an argument really quick where I try to cheat. So let's say I want to prove that if I know P or Q, then I know P. Let's get intuition for how this is false. And I'm going to prove it using our rules. So this says, true or false? I'm a billionaire or I'm a teacher. Is that true? Right, so the antecedent is true. The conclusion, I'm a billionaire. Is that true? No, so the premises was true, but the conclusion is false. So this is not a valid rule of logic. If you know P or Q is true, you cannot conclude P is true. All right, now I'm going to prove it. Let's do premise 1. So 1, I introduce as a premise P or Q. We use rule P, and it's only dependent upon 1 for its validity. I introduce as a rule 2, I introduce not Q. Or as my second premise, that's a premise, it's only dependent upon 2 for its validity. Now I know if I have P or Q, and I have not Q, then I have P. Right? So, 3, I can then conclude P, and that's tautologically implied by lines 1 and 2. So didn't I just cheat? Didn't I show that this implies this?
No, because you assumed something from your premises that wasn't there on number 2.
Perfect. All I showed is that P logically follows from whatever lines 1 and 2 had, these two premises. I did not show that follows from this premise alone. So your gut instinct might have been, if I can just introduce any premise I want, can't I just prove whatever I want? And the answer is no. So even though I can introduce any premises I want, all I'm showing is whatever premises I introduce until my conclusion. So that's why you can introduce any premise you want.
We have to have the premise in the...
Well, the point is that this does not prove this statement.
Yeah.
What did we prove here? We proved that if you know P or Q, and you know not Q, then those together imply P. That's what we proved here, which is very different from this. And if you tried to prove this, you'd never be able to do it. So this can't be proved. So I know that the first time I read that, my first gut reaction was, that makes it seem like I can prove whatever I want. And the answer is no, you can't. Logic works. All right, let's do another example of a full proof. Need to find wherever he says example 2. It keeps jumping on me every time I turn off that projector. That was the example? No. Oh, so that's him doing example 2. All right, we don't want to look at his work, no cheating. We want to think about ourselves. Okay, so our next example, here's what we're going to prove. If the Cards are third, then if the Dodgers are second, the Braves will be fourth. So I'm going to use C for the Cards are third. So C will be the Cards are third. I'll use D for the Dodgers are second, and B for Braves will be fourth. So we know if the Cards are third, then that implies if the Dodgers are second, the Braves will be fourth. What was it, Dodgers? Dodgers implies Braves. Kind of a messy statement. There's the logic of it. It's saying, if this is true, then, if this is true, this is true. Read that one more time. If the Cards are third, then, if the Dodgers are second, the Braves will be fourth. See how we're encoding that? Let's encode the next one. Either the Giants will not be first, or the Cards will not be third. Or the Cards will be third. Yeah, don't let me screw up my notes here. Hard for me to read this close on this angle. Either the Giants will not be first, so either not Giants or Cards. Did I do that right? Thank you. And then, in fact, the Dodgers will be second. So we know D. Therefore, if the Giants are first, then the Braves will be fourth. So we're trying to show Giants implies Braves. That's what we're trying to prove. Let's get this out of the way. Now we have all that. Giants implies Braves. I'll write that higher. So here's what we're trying to prove. We're trying to prove if Giants, then Braves. Once again, these are going to be my premises. I introduce this with rule P. We'll come to the side more. And it is only dependent upon one for its validity. This I introduce as a premise. It's only dependent upon 2 for its validity. This I introduce as a premise. And it's only dependent upon 3 for its validity. Right? Okay. Now, how do we start this? This time we're trying to prove an implication. How do you prove an implication?
You assume the antecedent?
You assume the antecedent and show that implies the conclusion. And that is going to be using this rule CP here. So introducing this rule CP, our third rule of logical derivation. Our third rule of deductive reasoning here. Rule CP says, if we can derive S from R and a set of premises, trying to do fancy P there, so P could be one premise or many, all ANDed together, then we can conclude R implies S from the premises alone. Intuitively, here's what this is saying. Wrote the truth table here for it. If knowing P and R is enough for us to conclude S, then knowing P is enough for us to conclude if R then S. And these are logically equivalent. Let's fill out the truth table really quick. All true here means that this is going to be true, and this will be true. All right, this one is true and true is true, implies false is true and false is false, implies anything is true. False implies anything is true. False implies anything is true. False implies anything is true. 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 Good so far on that one?
Is that column P and R implies S or P and R implies S? Okay.
Yeah, you'll get used to that, but I usually only bother with parentheses for distinguishing between ands and ors, but just so you remember, your precedent is right here. You do not set ands and ors and implies then if and only ifs. Okay, so now let's look at this one. So first off, R implies S is, true implies false is
False.
false, and true implies false now. True implies false is
False.
false. Let's see. False implies true is,
True.
and then true implies true is true. False implies false is,
True.
and then true implies true is.
True.
And then for all these other ones, fancy P here is false, so they're all vacuously true. And so that's the idea behind this rule. That doesn't prove the rule. That's the idea behind the rule, because P here could be some conjunction of many premises. And so I can't do a truth table for it, because P could be ANDing together premise 1 and premise 2 and premise 3 and premise 4. But the point is, if I know all my premises together with R implies S, then I know my premises alone implies the fact that R implies S. And so now, here's how we use this rule of conditional premises. CP for conditional premise. I'm going to introduce as a premise G right here. We indent it. I'm using rule CP. This is a conditional premise. And now it is dependent upon 4 for its validity. Good so far? Think about it this way. I am allowed to introduce a premise at any point. So CP is actually going to be how I can get rid of that premise when it's all said and done. So for now, I'm just going to introduce a premise P. You might think I'm cheating. I have to remove this premise before it's all said and done. Otherwise, I've cheated. Okay, let's keep going. So, and then this is logically equivalent when you're doing geometry proofs. You say, let da-da-da-da-da. You assume the antecedent. That's essentially what we did thinking in terms of mathematics. Okay, so now, there's our next premise. So if I know G, now what do I know?
Not C, or wait, no.
You're so close. I know G is false or C is true. Is G false?
No.
Then,
C's false.
let me say it again. I know G's false or C's true. Is G false?
No.
So C is
True.
true. There, and connected. So now we know C. This is tautologically implied by 2 and 4. So we're using rule T here, 2 and 4. And now it is dependent upon, for its validity, lines premises 2 and premises 4. With me? Okay, so now we have C. What can we conclude?
DB, or D implies B.
D implies B.
So B.
Well, we'll do it one step at a time, but you see the next step. So I know C implies this, and I know C. So 1 and 5 tautologically implied by 1 and 5 gives us this, and we are now dependent upon, for our validity, lines 1 and, or premises 1, 2, and 4. Right? Good so far, no cheating? Except you don't like when I introduce that, but I promise we'll fix that. Okay, so now I know D implies B, and I know D, so what can I conclude?
B.
B. I know if D is true, then B is true, and I know D is true. So 7, I can now say B is true. And this was tautologically implied by lines 3 and 6. And so now we are dependent upon, for our validity, lines 1, 2, 3, and 4. Now, here's where I'm going to use this rule. If we can derive, in our case, this is going to be S, and this is going to be R. Let me just rewrite this using R symbols over there. If we can derive B from G and a set of premises, fancy P. In our case, what's fancy P? It's this and this and this, all ANDed together. Then we can conclude G implies B from the set of our premises alone. So I can now, using rule CP down here on 8, I can now conclude that G implies B. This was using CP, and we write the line where we started to where we ended, 4 to 7. 4 to 7, and we are dependent upon for our validity now 1, 2, and 3. We removed G as a premise. It's no longer a premise. We're no longer assuming G is true. We're just saying if G is true, B is true. Because that's what we showed here. We showed if you introduce G as a premise, then you can conclude B. So what we've shown when it's all done is that if G is true, then B is true. And that's what we've shown. And so we are no longer using 4 as a premise. So we introduce it as a conditional premise, and then we get rid of it before everything's said and done. Any questions on that?
I don't understand how you can just decide this conditional premise. I understand you explained that, and then you wrote a G. I don't understand the connection.
Okay, let me continue here. What was R? R was G. B. R was G. And B. G. B.
G is.
And G and B here.
And P is the conjunction of all of the premises.
And fancy P, in our concrete case here, fancy P would be equal to C implies D implies B, and not G and C.
Or you did the wrong. It's 4.
Oh,
Yeah.
thank you. And D. Here's what fancy P would be in this case. The conjunction of all our premises.
Yeah,
Also, the P is on the truth table.
you didn't finish writing your B. You went back up.
I didn't finish writing my what?
Fancy
Your B.
P on your truth table, G, P. You meant to write a B. Over on
At
the
the,
left.
on the third row. Or
All the way. The red.
column.
Column 4. You have G, P. You need it to be a B.
And R was G, right?
Yeah.
Okay.
Yeah.
Here's refilling our truth table in this concrete example.
Yes.
So if I know fancy P and G implies B, then I know fancy P alone implies G implies B. So if I take my set of premises and I end G as a new premise, I was able to conclude B.
Why did you decide G of all the premises?
That's the premise we used here.
Starting with the end in mind.
I was trying to show G implies B.
Oh, okay, gotcha.
So this was big picture what we were trying to prove.
Okay.
I wasn't trying to prove B is true. I was trying to prove G implies B is true. If the problem asked me to prove B, I would have been stuck. There's no way to do it. All I could show is that if G was true, then B would have been true. And so showing the premises and G being true implies B is true is the same thing as showing the premises imply G implies B. These two columns are logically equivalent.
Yes.
Now the reason that this doesn't count as a rule of logic is because P here isn't anything well defined. In this case, it was a conjunction of all these things. What if I had 100 premises? Well, then it's a conjunction of 100 premises. And so there's a bit of fuzzy thinking there that isn't very precise like truth tables are. And so it has to be introduced as a rule of derivation, and it can't just be some rule of logic that we're using. Because I can't come up with a truth table that shows us this is true. This truth table is just to give you intuition. Because I didn't separate out all the P's, all my premises. Because I can't. Because I'm saying it's true if you have 1,000 premises. I'm saying it's true if you have one premise. Make sense? So there's some concrete examples doing proofs. So next week we'll get much more comfortable doing proofs. And then the week after that we'll go through the actual grammar of logic. Because right now the way we're symbolizing these sentences is very coarse. We're taking a whole sentence like the sky is blue and we're representing it with a big S. And that sentence has a lot more structure than that. So we'll get more comfortable with proofs, and then we'll look at the sentences on a finer level and look at all their logical structure instead of just kind of this big picture logical structure. So that's what we have upcoming. Any questions that you want recorded?
Why do we call them criterions?
It's just some criteria that we want them to follow. We for sure want whatever our rules of logic are to do these two things. It's like we're almost pretending that we're building up logic ourselves. And what would we want to make sure happens? That's one way to think about it. Anything else? Cool. We'll call it there. And
Can we talk about switching class to Monday?
oh yeah, where's
I didn't
Jeremy?
think we did record it, but I wanted to.
Yeah, we can turn that
I
off.
was gonna say